Welcome back to this video series where we go through Betaflight 4.3 configurator, take a look at every single option and tell you what it is and how to set it up so you know how to do it when you encounter it in the real world. If you've randomly stumbled across this video, it is part of a series. There's a link to the playlist down in the video description, and it's really intended that you would start at video number 1 and work your way through the whole thing. But if you are here for the power and battery tab, that's what we're looking at today. Let's do it. And in some sense, the power and battery tab is the most important tab in Betaflight because it tells you when your battery voltage is getting to be too low and you're about to damage your battery, or your battery's going to sag out and you're going to lose your quad. This video is not specifically about LiPo voltage management, but the bottom line is that when a LiPo battery goes below about 3.0 volts per cell, it takes permanent damage. But more importantly, when a LiPo gets close to or below 3.0 volts per cell, the voltage drops off rapidly and your quadcopter stops flying. And depending on where you are, you can just lose your whole quad, you can crash your quad, you can damage your quad. You want to you have to monitor your LiPo voltage while you're flying. And without the options in this tab, you just can't do that. So every flight controller today is going to have the ability to monitor the voltage of the battery that's plugged into it. And you can see right now, it says state connected, no, voltage 0.02 volts. And that's because right now we do not have a battery plugged in to this flight controller. So instead, let's switch to an actual flight controller plugged into an actual quadcopter and plug a battery in and go from there. Now you can see that the power state has changed to connected, and we have a pack voltage being shown here, 16.82 volts. Now let's talk about the construction of a battery because it's relevant to what we're seeing here. This is a 4-cell battery, which means it has 4 individual LiPo cells. Each of those cells has a voltage between 3.0 and 4.2 volts, and they're wired in series, so that voltage adds up. And that voltage is what Betaflight sees coming out of the XT60 here. And you need to understand that that pack voltage of 16.8 volts is the only thing that Betaflight can see. Now, Betaflight will use that number to try to guess about the number of cells that the pack has. And that's relevant because Betaflight also wants to show you the average cell voltage. If you fly with 6S, 5S, 4S, 3S, if you fly with a whole bunch of different pack voltages, it can be a little bit annoying to have to remember what is 3.0 volts per cell? What is the point where I have to turn around and fly home or my battery is going to be too low? Instead, it's much simpler to just remember 3.5 volts per cell is where I turn around. And Betaflight can show you that average cell voltage in the OSD, but it can only show you that if it knows the number of cells. So Betaflight tries to figure out the number of cells. For a 4-cell battery, when you first plug it in, if it's at 4.2 volts per cell, and that's going to be around 16.8 volts. So when you plug in a battery and Betaflight sees that it's around 16.8 volts, Betaflight just guesses that this is probably a 4-cell battery. Now, it's important to know that Betaflight can get it wrong sometimes. If you have high volt cells, which are charged up to 4.35 volts instead of 4.2 volts, then Betaflight can mistakenly read that fully charged 4S as a almost fully discharged 5S. And when you first plug in, Betaflight might misread the number of cells. We'll talk about how to configure that a little bit later in the video. So when we first plug in, Betaflight is going to give us this voltage reading, and it's going to calculate the cell count. And we can also see that voltage reading up here at the top of the screen. And of course, we would also see that in the on-screen display in the goggles and so forth. How does Betaflight know that number? Every flight controller is going to have a voltage source. And you can see here that the default voltage source is onboard ADC. ADC stands for analog to digital converter. It is a type of sensor that takes the analog voltage and converts it into a digital number that Betaflight reports to you. And for almost every flight controller, the correct value for the voltage meter source is going to be onboard ADC. The flight controller designer has designed the flight controller to read the voltage from its onboard ADC. When would you not use onboard ADC? So if we have a BL32 ESC like this T-Motor F55A Pro, and if that ESC supports BL32 telemetry, then it can report battery voltage through the BLHeli32 telemetry. How do you know if an ESC supports BLHeli32 telemetry? Well, first of all, it has to be running BLHeli32. If it's running BLHeli-S, then this doesn't apply. And if we look at the pinout diagram for this ESC, we can see that there is a telemetry wire coming out of the ESC. Sometimes that wire will be labeled telemetry, sometimes it'll be labeled T, sometimes it'll be labeled TX, but the bottom line is it has a telemetry output that connects to a UART on the flight controller, and we talked about this way back in part number 2, I think it was, the ports tab, how you would set up ESC telemetry. If your ESC supports ESC telemetry, then you can change the voltage meter source to ESC Sensor instead of onboard ADC. Voltage values, in that case, you would see the voltage values for each individual ESC as well as the combined value. Now, why would you want to do that? The main reason that you want to do that is that most flight controllers only support an input voltage between 2S and 6S. And if you're using a higher voltage battery, specifically if you're using a Cine lifter and you're running 8S or 12S, or if you're using a Beast class or X class quadcopter, anytime you're using higher than 6S voltage, your flight controller probably cannot take that voltage natively and therefore cannot sense the voltage. You're going to be running it off a voltage regulator, like a 12-volt regulator, at which point, if you're feeding the flight controller 12 volts input voltage, then it will just read VBAT as 12 volts all the time, and you won't know what your actual battery voltage is. In that case, you would be using an ESC that could run off of your native voltage, because they always do. And in that case, most ESCs that run off of higher than 6S voltage will also support ESC telemetry to allow them to report the voltage back to the flight controller, and that is when you would typically use this function. The other time when you might use ESC Sensor would be if for some reason, like the voltage sense circuit on your flight controller has been damaged and it's just stopped working. And in that case, ESC Sensor could be a workaround for that, although that's a pretty rare circumstance. Now, there's another little quirk with voltage sensing that I want you to be aware of just in case you run into it. Most flight controllers, like we'll take the JBF7 for example, most flight controllers are designed so that they have a plug that goes to the 4-in-1 ESC. The ESC feeds VBAT into the flight controller. That battery voltage both powers the flight controller, and that exact same wire or pin is used for voltage sensing. Okay? But not all flight controllers work this way. So if we take a look at the Brain FPV Radix flight controller, it has two separate pins. One of them is for power, which is labeled as 8S max, and one of them is for VBAT sensing, which is 12S max. And this is a little confusing because on flight controllers that use VBAT and power as the same thing, they'll just typically be labeled VBAT, and there isn't a separate power input wire. So you got to read the documentation. But in this case, we could power the Brain FPV Radix from 8S, but we could have voltage sensing up to 12S. And depending on the status of the power VBAT jumper, those might be the same thing or they might not. So make sure to read the documentation of your flight controller to see what the maximum input voltage of the flight controller is, and just to confirm that VBAT input is also voltage sensing, or whether voltage sensing and power input are a separate function. But on most flight controllers, the VBAT input from the 4-in-1 ESC is also going to be used for voltage sensing, and it's going to be very simple to wire them up. Next, let's discuss the minimum, maximum, and warning cell voltage parameters. The warning cell voltage is the average cell voltage where Betaflight starts beeping. You'll literally hear the beeper start going beep, beep, beep while you're flying. And if you've got an on-screen display, you'll see a warning pop up in your on-screen display telling you your battery is starting to get low. 3.5 volts is a great value for that. The only time I would change that value is if I'm flying a tiny whoop with a little 1S 300 milliamp hour pack. Those packs, they have so much voltage sag that you basically have to run them down to 3.0 or 3.1 volts per cell, or you just don't get any flight time. So for a little 1S 300 milliamp hour pack like a tiny whoop, I would lower this warning to about 3.3 or maybe even 3.2 volts. But for most packs, I would have 3.5 volts as the warning. the minimum cell voltage and the maximum cell voltage, you might think, well, minimum cell voltage is where the quadcopter will like shut down or stop flying, and that's not the case. It'll just keep flying until the battery dies. But the minimum cell voltage and the maximum cell voltage are used in the calculation of what is the number of cells of this battery. So we can see here that the voltage of this pack is 16.6 volts. And if I take 16.6 and divide by 4, I get 4.15 volts per cell. Let me unplug this again. I'm going to change the maximum cell voltage from 4.3 to 4.1 volts. And you can see that this is going to come in at over 4.1 volts per cell. Let me just save that, and then I'm going to plug in. And when I do that, notice that now Betaflight calculates this as being a 5-cell battery instead of a 4-cell battery. Right now, Betaflight thinks that this is a 16.6 divided by 5. Betaflight thinks that this is a 5S battery at 3.3 volts per cell, not a 4S battery at 4.2 or 4.15 volts per cell, because we have told Betaflight that the maximum cell voltage it should expect to see is 4.1 volts, and that is the only way for Betaflight to make sense out of the voltage that it's seeing. So this maximum cell voltage and minimum cell voltage are used by Betaflight to try to figure out how many cells are in the battery that it's seeing. So let me unplug this again, and you might think we should set this to 4.2 volts, because the closer this is to like the real numbers, the more likely Betaflight is to accurately calculate the number of cells that are in the battery. And that's not quite true. Usually when you first plug in, there's a little bit of a voltage spike, and then the voltage settles down. So you don't want this at 4.2 if you're using regular LiPos. You want it at maybe 4.25. And if you ever use high volt batteries that charge to 4.35 volts per cell, like again, Tiny Whoops typically will charge to 4.35, you would set this to 4.4 if you're using high volt cells, or 4.25 or maybe 4.3 if you're using standard LiPos. And as far as the minimum cell voltage goes, again, that also pertains to the warnings that you see on screen. You would leave it at the default for typical LiPos, or for those little 1S Tiny Whoop cells, I would set it to 3.0 and maybe 3.2 or 3.3. And that is how I would set those values. Next, we come to current sensing and the current meter source. And voltage sensing is a little bit intuitive, like it's just how many volts the battery is putting out. And when the battery is at 4.2 volts, it's full, and when it's at 3.0 volts, it's empty, and that's just it. Current sensing is how many amps are being pulled from the battery at any given point in time. And if we were to make an analogy to like a gas tank on a car, if the voltage is how full the gas tank is, then the current is how fast the fuel, the flow rate, the gallons per minute that is coming out of the gas tank. And amps is relevant, current is relevant, because the more current you're pulling from the gas tank, the faster it's going to be empty. But in addition, each battery has a certain C rating that relates to how many amps you can safely pull from the battery. So if you know you've got a battery that's rated for 70 amps, you might be interested in knowing how many amps your quadcopter is pulling at any given time to see if your battery's C rate is adequate. But that's not actually the main reason to care about current reading. The voltage can tell you when a battery is fully charged and when a battery is empty. But it's not good at telling you how close you are to being empty. And the reason is that a battery's voltage drops off in a very nonlinear way. At the very beginning of your flight, your battery drops from 4.2 volts right down to like 3.9 volts. And then it kind of plateaus. There's this long plateau where the battery voltage stays around 3.9, 3.8, 3.7. And then right at the end, the battery voltage drops off abruptly. And that's fine if you're flying, like if you're racing, and when you're done, you just fly back, land your quad, and put a new battery on. But if you're doing like a long distance flight where you might be 5 kilometers out, and you need to know, do I have enough gas in the tank to get home again? Or am I going to go 3.7, 3.6, 3.543, and then I'm going to just lose my quad somewhere out there 5 kilometers away? So the real reason that current readout is useful is that current readout can tell you, my pack is capable of delivering 1,000 milliamp hours of capacity. I have consumed 500 milliamp hours, and that means I am at half tank. And if I need to come home, I need to turn around right now. That's what voltage is bad at, and that's what current is good at, and that's why people want current readout. Now, the first thing you need to know about current readout is that not every flight controller and ESC are going to be able to read current. Pretty much every flight controller out there today is set up to read voltage. It's very simple to read voltage. But number one, current reading is typically done by the ESC because the ESC is actually, the current of the motors is passing through the ESC. So it's very easy for the ESC to read current. The current of the motors is not typically passing through the flight controller. So the flight controller can't read the current directly. So typically the ESC will read the current and the ESC will report the current to the flight controller. If we go back again to this T-Motor F55A Pro ESC, you can see that there is a pin here, current sensing, and that is going to give the current information to the flight controller. And if we again look at this pinout for the JBF7 flight controller, in the 4-in-1 plug, there is a current sense input wire, and those two wires would be connected together, and the ESC would feed the information about the current that's being drawn to the flight controller over that wire. Here is another random ESC that I pulled up, the Acon AK32 ESC. And again, if we look at the pinout for this one, there is a telemetry and a current wire, just like the T-Motor. Now, not every ESC is going to have both a telemetry and a current sense output, but most ESCs today have at least a current sense output. You may come across an ESC that doesn't have a current sense output. They're pretty rare, but they do exist, and in that case, you just would not be able to do current sensing with that ESC. You just would have to go without that information. It's not the end of the world. Voltage will tell you when your battery is about to die. It just won't tell you how close you are to your battery dying with a lot of precision. So if your flight controller and your ESC have a current wire that is connected together, you will select onboard ADC as your current meter source, and then you'll be getting that information from the ESC to the flight controller. But that brings you to the next problem, which is calibration. So the ESC is reporting current to the flight controller as an analog voltage value between 0 and 3.3 volts. And the problem is, how many amps does 3.3 volts represent? And that's not going to be the same for every ESC. The best case scenario is that the manufacturer is going to give you amperage meter scale and offset value to put into Betaflight. Let's go back and check this T-Motor F55 and see if they give it to us. So here's the number that we actually need. 15.2 millivolts per amp. They could be more clear about that, actually what that is. Let's see, 1/110th of a millivolt per amp. So I think we would set this to 152, which is 15.2 millivolts per amp, and that would be the calibration information we would need for this ESC. What about our Acon? Current scale, 210. So for the Acon ESC, we would put in 210 as the scale, and that would get our current to be roughly calibrated. The takeaway here is that the current scale and offset depend on the ESC, not the flight controller, and you have to get that information from the ESC manufacturer. You might think that if you have a T-Motor flight controller and a T-Motor ESC, then that current scale would automatically be filled in, and it might, but it might not. You can't always assume that, and you always have to go back and check this. And another takeaway is that oftentimes when you first set up an ESC and a flight controller, the current values you see are completely bogus. You'll see, 30 amps just sitting there disarmed on the ground. And it's just clearly not right, and it's miscalibrated, and you got to get this value set correctly. Now, there is a calibration button down here in the lower right. If you don't have information from the manufacturer about what the correct calibration value is, and if we hit that calibration button, we have the option to calibrate the voltage and the current. But before we do that, we need to plug the battery in. So let's plug the battery in. And now that we've got a battery plugged in and we hit calibration, we have the option to measure the battery voltage. So I'm reading a voltage here of 16.43 volts. I know this cell checker is accurate. I've tested it, or let's just assume it's accurate. I'm going to put in 16.42 volts here and hit calibrate. And it's going to calibrate a voltage scale for me, and I can hit apply calibration, and now my voltage is calibrated. Yay. Now, it turns out that calibrating the current is a little more complicated than calibrating the voltage, because measuring voltage is easy. I just did it with a little cell checker. Measuring current is harder, and measuring current precisely is harder still. There's a method for calibrating the current scale, and what you do is I've got a tutorial about how to do it. I'll put a link to the full tutorial in the video description. The short version is that you fly the quad, you see how many milliamp hours Betaflight reports that it used, you recharge the battery, and your charger shows you how many milliamp hours it put in. You trust that the charger is accurate, and then you calibrate Betaflight to the charger. There's a link to a full tutorial about how to do that down in the video description. The bottom line is, if you can get the scale value from your manufacturer of your ESC, you totally should. And if you can't, there's a process for doing it, but it's a little bit time consuming. What about this line here? Warning, values limited to 25.5 volts. Warning, values limited to 63.5 amps. There is a relationship between the scale and the maximum value that the sensor can read. And the reason for this is that the actual sensor signal is coming into the flight controller with a maximum voltage of 3.3 volts. It's between 0 and 3.3 volts. So if each fraction of a volt represents 10 amps, then you could read up to 330 amps. 10 amps times 3.3 volts is 330 amps. If each fraction of a volt represented 5 amps, then you could only read half that value. And the takeaway here is that this is not something you can control. This is a parameter that is set by the manufacturer of the ESC and the flight controller, but you do want to be aware that, well, this maximum scale with a scale of 109, the maximum voltage we can read is 25.5 volts. Well, that's fine. That's a 6S battery. It doesn't really matter. That's not going to hold us back. But the current scale, the amperage meter, it is going to matter. So if you had an ESC with a current scale of 400, the maximum amps it could read would be 63 amps. And that would be a problem because many flight controllers, many quads are going to pull more than 60 amps. And you would just max out at 60 amps and that would be inaccurate and that would be a problem. If we change this value from, say, 400 down to 200, we should see this maximum value double from 63 to 127 amps. Let's just save that. I didn't change it all. I think that's a bug. This should be showing the maximum value of amperage that you can read. And as the scale goes down, this should be going up proportionally, and it isn't. That's a bug, I think. My memory is that a scale of 400 is about 60 amps max that you can read, and then so proportionally as the scale goes down, that should go up. This is relevant because if your manufacturer says that your current scale is 210, like that Acon ESC, the maximum it could read would be about 120 amps, which some flight controllers are going to exceed that. On the other hand, the T-motor had a scale of about, I think it was 150, and that would give you proportionally higher, something closer to about 300 amps, which is more than most people are going to need. What's left on this page that we haven't talked about? There are a couple other current meter sources that we should talk about. ESC Sensor. So if you have an ESC that does BLHeli32 ESC telemetry, then it could report current through BLHeli32 telemetry. Now, we've been talking about reporting current from the ESC using analog current sense wire. What's the difference between reporting ESC via analog current sense and reporting current via ESC telemetry? One advantage is that if you were using ESC telemetry, then all of the calibration of the current sensor would have been done by the manufacturer of the ESC. You would not need to mess with any of the calibration values. And you can see here that when I change this to ESC Sensor, all that calibration crap goes away and we just have current readings straight from the ESC. However, most manufacturers of ESCs do not do this. There was a time when they did, and the reason that they don't is that when they do this, they need 4 separate current sensors, one for each ESC, and it just means that the ESC is more cumbersome, more expensive to build, and rather than have 4 separate current sensors, one for each ESC, they would rather just use analog current sensing and report it to the ESC with a single current sensor. So most of the time, even if you have an ESC that does BLHeli32 telemetry, if you choose ESC Sensor, you will not get any readings from the ESC. It'll just read 0 amps and it won't work. So most of the time, this won't do anything for you. The virtual current sensor, what that does is it tries to guess how many amps you're pulling based on your battery voltage. And if this is calibrated correctly, it can be pretty accurate. But the problem is that if you change anything about your build, you use a heavier battery, a bigger battery, a different manufacturer, make or model of battery, it can throw off the calibration and make this inaccurate. If you're interested in setting up the virtual current sensor, there is a link to the Betaflight GitHub page that shows how to do it. I'll put that link in the video description, but you have to be aware that the virtual current sensor is only accurate once it's calibrated, and if anything changes, it won't be accurate anymore. So be really careful about relying on the virtual current sensor. It's much better to have an actual current sensor if you really need that. Next up, we are going to talk about the failsafe tab. What does your quadcopter do when you lose link, and ways to configure that? There is a link down in the video description to this full playlist, and if that video is out, it'll be there, or I'll put a card on screen to that video once it's out, or a card on screen to the full playlist. Thank you so much for watching. I'll see you there.